Sonia, can you hear us? Okay, great.
Yes,
okay.
I can hear. Can you see my screen?
So we have Sonia Boscolo from Birmingham, and she's talking remotely on complex nonlinear wave dynamics in ultrafast fiber lasers and their intelligent control. So please.
First of all, I would like to thank the organizers for having invited me. And I'm really sorry that I cannot participate in person because I got COVID recently and I'm not still fully recovered. So this talk is a bit outside the main topic of this workshop. I will speak of the machine learning control of complex nonlinear wave dynamics in ultrafast fiber lasers. And this talk is in collaboration. I would like to thank my colleagues, Junsong Peng from East China Normal University, and his colleagues, and Christophe Finot from the University of Bourgogne in Dijon, France. So let's start with saying that model-locked fiber lasers are well known to display a rich landscape of dissipative solidon dynamics that results from the interplay of the nonlinearity with the dispersion and dissipation. And here you can see a typical ring fiber cavity that includes again fiber, other kind of fibers, and the polarization controllers that facilitate the model locking of the laser through the nonlinear polarization evolution effect in the fibers. The various solidon dynamics that have been observed include breeding of pulsating regimes, solidon explosions, chaotic pulse states, formation of rogue waves that are pulses of giant amplitude analogous to the frequent oceanic waves, as well as various multipulsing regimes where the interactions between the solidons lead to harmonic model locking or self-organized patterns, such as stable multi-solidon bound states that are also called solidon molecules and solidon molecular complexes. And although several of such dynamics have been studied theoretically for many years, their properties have recently received renewed attention because of the development of advanced measurement techniques that enable their single-shot measurement in real time, which therefore allow round-trip variations in pulse characteristics to be observed, which is not possible with the traditional measurement tools. And the technique of this kind that is particularly straightforward to implement experimentally is the time stretch dispersive Fourier transform, which in the context of fiber lasers enables measurement of round-trip resolved spectra. The method maps the optical spectrum of the laser output onto a temporal waveform that is directly read out on a real-time oscilloscope. And this is achieved by stretching the laser pulses in a dispersive medium that accumulates a group velocity dispersion large enough for the pulse propagation to satisfy the far field condition, and so for the stretched waveform to represent the spectral intensity of the initial pulse waveform, which is the temporal analog to the far field of Fraunhofer diffraction. And in terms of numerical modeling, we here use a discrete model for the laser, which models each part of the cavity separately. Pulse propagation in the optical fibers is modeled by a generalized nonlinear Schrödinger equation for the slowing bearing pulse envelope in the scalar field approach, which includes the effects of group velocity dispersion and self-phase modulation for all the fibers, and gain saturation and bandwidth limited gain for the active fiber. And the discrete effects of the effective nonlinear saturation involved in the NP model locking are modeled by an instantaneous monotonous nonlinear transfer function for the field amplitude as in here. Now, reaching a desired operating regime in a fiber laser generally depends on precisely adjusting multiple parameters, which is usually performed through a trial and error experimental procedure. And the difficulties associated with such a procedure can be overcome by machine learning strategies, specifically the use of evolutionary genetic algorithms, which are well suited to global optimization of complex functions. And the general approach, as illustrated here, is to combine an algorithmic feedback loop together with the electronic control of the intergravity elements that vary the parameters of interest, in our case, the polarization state. So the operation state of the laser is characterized in real time with a measurement system, the oscilloscope, which is connected to a computer that runs a genetic algorithm and controls the polarization state through the voltages applied on an electronically driven polarization controller. And the genetic algorithm principle illustrated here mimics a mechanism inspired by the biological evolution. In our case, an individual is a laser state associated with the DNP transfer function defined by the control voltages applied on the polarization controller, which are therefore the genes of the individuals. The process begins with a randomly created population of individuals that make up the initial generation. Then the output of the system is measured for each individual in the generation, evaluated by a user-defined merit function and assigned a score. And then the genetic algorithm creates the next generation by breeding the individuals from the preceding generation. And two new individuals or children are created from the crossover or two randomly selected parents. And we specify also a mutation probability, which allows for the genetic sequence to be refreshed. And the process repeats until the algorithm converges and an optimal individual is produced. So in this talk, I will provide an overview of our progress in the control of non-stationary nonlinear dynamics in fiber lasers by using genetic algorithms. Specifically, I demonstrate that the fiber laser working in the breeding solitary regime is a system showing the frequency locking at the 5 refractions, where the frequency locked states occur in the sequence that they appear in the Fourier tree, and within a pump power interval that is given by the width of the corresponding step in the Davis staircase. And I will also report on the intelligent generation of optical log waves and control of their intensity in a fiber laser. So, breeding solitons are localized temporal or spatial structures exhibiting the periodic oscillatory behavior, are found in various subfields of nonlinear science. And in optics, they have recently attracted significant interest by virtue of their connection with a range of important nonlinear dynamics. Optical breeding solitons were first studied experimentally in a Kerr fiber cavity, subsequently reported in optical microresonators. And more recently, they have also emerged as a model of the regime of ultrafast fiber lasers, thanks to various studies that have revealed the fast spatial spectral and temporal dynamics using real-time detection techniques, as well as the self-organization of multiple circulating breeding solitons into various types of molecular complexes. More recently, we have also introduced an approach based on a genetic algorithm for the generation of breather dynamics with the controlled characteristics, which relies on specific features of the radio frequency spectrum of the breather laser output. And the merit function is the key ingredient of any genetic algorithm because it defines the optimization target. And this is here the merit function for the auto setting of the breather model locking regime. So here you can see that FML is the merit function related to the laser model locking operation, representing the average of the pulse intensities. And FB is a merit function that discriminates between the breather stationary pulsed operations, and it is derived from the feature that the breathing frequency manifests itself as two symmetric side bands, F plus minus 1, around the cavity repetition frequency in the radio frequency spectrum. So this merit function is designed to exploit the intensity ratio of the central band located at FR to the side bands at F plus minus 1. And here we have an example of an optimization curve showing the evolution of the best average merit scores of the population for each generation. And also we have summarized the spectral temporal characteristics of the optimal state. Specifically, you can see a radio frequency spectrum with the two symmetrical side bands around the cavity repetition frequency, and a periodic compression and stretching of the optical spectrum over cavity running strips, accompanied by synchronous periodic changes of the pulse energy, the peak intensity, pulse duration, and the time domain. And these are all distinctive features of the breather operation regimes. Now, by including additional components in the definition of the merit function, we have also achieved advanced control of the characteristics of the breather states, such as the oscillation period, or the breathing ratio, which is the ratio of the largest to the narrowest width of the pulse spectrum within a period, and also using the same merit function, but at pump power levels favoring the multipulse self-starting of the laser, and subsequently applying the pulse count, we have generated the different types of breather molecular complexes with a controllable number of elementary constituents. Now, nonlinear systems with two competing frequencies show frequency locking or resonances, in which the system locks into a resonant periodic response, featuring a rational frequency ratio or winding number, and quasi-periodicity between locked states, where the process follows the hierarchy of the fiery tree and the structure of the David staircase, which is a self-similar curve with an infinite number of steps. Physically, the reason why the fiery tree is used to locally order two frequency resonances is that the fiery fraction is the fraction with the smallest denominator in the interval between the two adjacent rational numbers. So it produces the largest plateau, which represents therefore the most important resonance in the interval. And the fractal dimension of the Cantor set complementary to a complete David staircase was determined to be 0.87 for the staircase of the circle map. Now, frequency locking phenomena have been studied extensively in many physical systems, including modulated semiconductor lasers in the field of optics. But all the investigations so far relate to systems where an external accurately controllable modulation adds a new characteristic frequency to the system. In the case of breather oscillation in fiber laser, the second frequency, the breathing frequency, is not externally controlled and is intrinsic to the nonlinear system, which therefore shows a competition between the cavity repetition frequency and the breathing frequency. And here, for the first time, we have established the link between the breathing disorderance and frequency locking by benefiting from the genetic algorithm approach described before, and further developing it to directly pinpoint frequency docked breeders. So here we have an example of two different breeder operations over the laser, obtained at a slightly different pump powers. Sorry, in the top panel, the train of output pulses shows a periodic variations in intensity and spectral intensity as well, occurring across a well-defined period, which is in this example 5 cavity round trips. For the middle panel, the period of oscillations seems to be unchanged, but the quality of the periodic behavior is degraded. And the major difference between the two breeder states is revealed by the radio frequency spectra taken from an electronic spectrum analyzer. So you can see that the breeding frequency of the quasi-periodic breeder states exhibits a noisy and broad structure, while the stable breeder states feature a neat breeding frequency with a narrow line width and high signal-to-noise ratio. And this frequency is exactly equal to 1/5 of the fundamental repetition frequency, and so corresponding to a rational winding number of 1/5. So the merit function of the breeder model locking discussed before cannot distinguish between frequency locked and unlocked states, and it usually breeds unlocked states which have a broader parameter space. So for the genetic algorithm to tune the laser to frequency locked state only, we have defined a new merit function which takes into account the distinguishing feature of frequency locked states, that is a high signal-to-noise ratio of the breeding frequency. So here, the third term, FSNR, discriminates between frequency locked and unlocked breeder situations by evaluating the strongest breeding frequency in the interval of possible values for the breeding frequency. And here we have again an example of an optimization curve for a breeder state with a winning number of 1/5. And importantly here, we show the measurement of the breeding frequency of the optimal state under pump power and polarization tuning, slight tuning, which highlight the persistence of the optimal state, the frequency of the state, under system parameters perturbations. Now, using this approach, we have explored the transitions between the different breeder states of the laser that can be accessed by varying the pump power, starting from the range corresponding to a 1/5 frequency locked state. And here we have a plot of the breeding frequency as a function of the pump power that reveals the presence of various plateau steps. And the radio frequency measurements allow us to relate the breeding frequencies of the plateau to rational winning numbers. So in a frequency locked state, the radio frequency spectrum features a finite number n of equally spaced spectral lines below the cavity repetition frequency. The most important, the intense line in this comb is the breeding frequency. And if this is the M line from the short frequency side, then the corresponding winning number is M/M. Importantly, the winning numbers appear from left to right in the order predicted by the fairy tree, and the width of a given step depends on the level where the associated winning number appears in the fairy tree hierarchy. The gaps in pump power between the stairs refer to quasi-periodic breeder oscillations similar to the example that I shown earlier. And the calculated fractal dimension of the set of gaps is 0.906, which is close to the value expected from a complete David staircase. And the right panel here illustrates the build-up phase of frequency docking in the plane of radio frequency and pump power. Now, if we set the laser to a slightly different initial polarization state, we can find the Faraday fractions that belong to other parts of the Faraday tree when tuning the pump power. As you can see in these two examples here, and in both cases, the calculated dimension of the set complementary to the stairs approaches that of a complete David staircase. We have also performed the numerical simulations of the laser. So here you have the plots of the breathing frequency as a function of the gain saturation energy, which is related to the pump power in the experiment, when the latter is varied starting from the range corresponding to a 1/5 local state. So on the right panel here, we have used a smaller saturation energy variation step in the numerical model, and you can see more plateau, which therefore confirm the fractal structure of the winning number distributions. The model, you can also see that the model can reproduce the same part of the Faraday tree from a winning number of 1/5 to 2/9 as that observed in the experiment. The gaps between the stairs also are similar to that found in the experiment, and the fractal dimension of the set of gaps is closer to the value expected from a complete David staircase than the experimental value, because the steps in gain saturation energy can be made arbitrarily smaller in the model. So before I said that a small change in the initial polarization state of the laser can trigger Faraday fractions that belong to a different part of the Faraday tree, and we have confirmed these observations by numerical results here, which have been obtained by slightly changing the linear intercavity loss in the model. Now, the term optical log waves was introduced to describe rare pulses of broadband light arising during the process of a supercontinuum generation in nonlinear optical fiber. So in this context, they are characterized by an anomalous surplus in energy at a particular wavelength or an anomalous peak power, and they have been shown to follow heavy-tailed or also called L-shaped statistics in analogy with freak oceanic waves. Since their first observations and thanks to advances in ultrafast measurements, it has become possible to accurately measure the temporal spectral characteristics of their nonlinear evolution and also to control the initial conditions fed into the system. So extreme events in cavity-free optical systems are now well understood and are intimately associated with the modulation stability process solitons over a finite background. Log waves have also been observed in more complex systems with an optical feedback, such as fiber lasers, where the physical mechanism may differ from modulation instability related to dynamics. And here we demonstrate for the first time the possibility of using a genetic algorithm to promote the emergence and control the intensity of log waves, optical log waves. So here, in order to connect the merit function to the emergence of log waves, we first record a long time trace of the laser output on the oscilloscope, which enables through DFT measurements the accumulation of a statistically sound number of successive single-shot spectra, from which we can compute the distribution of the intensity maxima over cavity round trip. And then we design merit functions based on two common statistical criteria for a wave event to be classified as a log wave. One is that its height exceeds twice the significant wave height, defined as the mean intensity of the upper third of intensity peaks. Therefore, the corresponding merit function is FRW here, where CRW is the target intensity relative to the significant intensity, and therefore controls both the generation of log waves and their intensity. The other criterion is that Emax be greater than the mean intensity of the intensity peaks by 8 times the standard deviation from the mean. Super log waves refer to ultra large deviations from the mean intensity, so that this factor is 32. And therefore, the corresponding numeric function is FSRW here. And to be able also to control the intensity of super log waves, we have merged the two merit functions into a new one, FTSRW. And here we have an example again of optimization by the genetic algorithm, where you can see that after some generations after the optimal state has been first reached, the blue diamonds here, have smaller values of smaller fitness values than the target values. But the genetic algorithm then modifies the genes of the individuals, and the laser emits the target log waves again, which evidences the ability of the genetic algorithm to lock optical log waves. And these are also representative evolutions of the spectral intensity maxima of successive gravity round trips when the laser operates in the optimal ordinary and super log wave modes. So here I will show examples of on the left panel of statistical analysis for the observed ordinary and super log waves operations. So the histograms showing the distribution of spectral intensity maxima here computed from the DFT recording display the typical L-shaped profile of extreme events. We can also see that the peak intensity fluctuations in frequency domain are tightly connected with the changes of the pulse energy, which is computed by integrating the DFT spectra, and thereby entail a L-shaped profile of the associated energy distribution. And this qualifies the extreme events observed as temporal log waves as well. On the right-hand side, we have results of the tuning of the strength of the spectral log waves. We can see that the highest log wave generated has an intensity exceeding the significant intensity by a factor of 32.8, which therefore represents, to the best of our knowledge, the strongest optical log wave reported so far. And the bottom figure shows the distribution of the ordinary and super log waves in the plane of peak intensity and standard deviation. So we can make out from this figure that relatively low intensity events corresponds to super log waves when the standard deviation is quite small, while by contrast, high intensity events do not qualify as super log waves if the standard deviation is too large. So the intensity cannot be the only criterion to distinguish between ordinary and super log waves. Now, I think, so in our measurement, we have revealed 3 different generation mechanisms of log waves in our lasers. So frequency down or up shifting, transient noise-like pulsing, and temporal spiking preceding model locking. So here I will show briefly the typical log wave dynamics induced by frequency down or up shifting. So we can see that at the round trips here, preceding the emergence of the log wave peak, the spectrum features well-defined oscillations, while at round trips succeeding the log wave peak emergence, the spectrum structures is much more chaotic, seemingly noise-like, with significant changes from round trip to round trip, spanning a wider wavelength band. And the important feature noticeable here is the progressive frequency down or up shifting of the spectrum that occurs during the rising stage of log waves, So the stronger spectrum end at the start grows even stronger and develops into a spectral Rogge wave. And now to confirm this dynamics, we have performed the numerical simulations of the laser. Where
Can you come to a conclusion?
Yes, okay. This basically, this is the last slide. So the numerical simulations basically underlies a new physical scenario for the emergence of Rogge waves. So an initially asymmetric pulse, but coherent but asymmetric, causes one spectrum age to grow and evolve into Rogge wave to the effect of a self-phase modulation, while a concomitant intrapulse shock wave develops in the time domain, and this ultimately leads to pulse collapse and the emergence of noisy-like broadband structures similar to those observed experimentally. And this is the other two examples of Rogge wave dynamics, and these are my conclusions. And I would like to thank also our sponsors.
Are there any questions in the room?
Hi, Sonia, good to see you. So can I ask a very naive question? It's Karima speaking. So from the point of view of optical communications, are your Rogge waves good guys or bad guys?
Rogge waves are bad guys, there are instabilities. So in general, also breeding the solitons represents instabilities of the laser. So in practical laser designs, what you want is to achieve short pulses with high peak powers. So you would like to avoid such events, but at the same time, you can use fiber lasers as general platforms for investigating nonlinear dynamics, and that can be of interest for other fields. For instance, in the case of Rogge waves, but this is valid also for the breeding solitons demonstrated. So for the first time here, we demonstrated the possibility of actively controlling the intensity of Rogge waves. Now, the merit function that we use, as you see, is very general, is based on statistical defining criteria for Rogge waves. So the same approach could maybe be used in other physical systems to generate and study Rogge waves, such as, for instance, water tanks. The same applies to breeding solitons. Breeding solitons have also found different applications, because when you generate so at the point in the round trip in the period of oscillation, so where the peak power is at the highest, you can imagine to output the laser and so create a high peak power pulses without the need for additional compression tools outside the laser. Or they can
Maybe may I suggest that you have a chat with Karima some other time. Thank you.
Sorry for being long. Thank you.
Okay, so thank you again.
Thank you.